Hello and welcome back to our video lecture series. In this set, we're going to start talking about linear regression modeling. In particular, we're going to look at ordinary least squares regression modeling, or what is generally referred to as OLS. Regression modeling refers to a class of statistical models that allow us to examine the effect of one or more independent variables on a dependent variable. Regression modeling is a little bit different than some of the tools we've talked about, like chi-squared and difference of means testing, in that regression modeling allows us to make predictions about outcomes. That is, it allows us to model the relationship between an independent variable x and a dependent variable y, and allow us to predict values of y based on values of x, even if those values of x and those values of y are not observed directly in our sample. For this reason, regression modeling is sometimes referred to as predictive modeling or predictive analytics, where we refer to the independent variables as regressors or predictors of the outcome. So for our purposes, we're going to focus on linear modeling, which is the assumption that the relationship between x and y is a straight line. There are a lot of other models that allow you to evaluate nonlinear relationships, such as a logistic relationship, which would be shaped like an S, or a curvilinear relationship that may be shaped like a U. However, we're going to focus solely on the existence of two possibilities: that the relationship between x and y is positive linear, that is, as x increases, y also increases, or negative, as x increases, y decreases. The null hypothesis for any regression model is generally going to be that the slope of the line is 0, meaning that as x increases, there is no change in y. We'll cover all these more specifically in our subsequent videos, so let's jump into how OLS regression works for a continuous dependent variable and a continuous independent variable now.
All right, let's jump into looking at how we do linear modeling with OLS regression. So keep in mind here that we're starting out with two variables that are both continuously measured, a dependent variable y and an independent variable x. For the data that I've collected here, I've got 20 students, and I measured for those 20 students their score for midterm grades for a section of POL 509, Approaches and Methods in Political Science, and their final exam score for POL 509. My question here would be, is there a relationship between midterm scores and final exam scores? And can I use students' midterm scores to predict how well that these students will do on the final exam? So basically what OLS regression is going to do is it's going to take the data points that you're feeding into the model, and it's trying to assess what type of relationship, in this case, what type of linear relationship exists between those data points. So just to visualize, if you take the midterm grades and final exam grades and you create a scatter plot, which I've shown here, most people kind of see that there's a linear relationship where as midterm grades increase, final exam grades also increase. So the purpose of regression, or what the regression analysis does, is it takes that data that you fed into the system and it figures out what line best characterizes that set of points. So keep in mind from algebra that we can define any line as saying y, or dependent variable, is equal to some slope coefficient times x plus some y-intercept. In algebra, we reference that as y equals mx plus b, where m referred to the slope of the line and b referred to the y-intercept. In statistical notation, it's a little bit different, but it means the same thing. So in statistical notation, we have a dependent variable y equal to Greek letter beta. Beta is our slope. Once again, we used m in algebra. We're going to use beta for our slope in statistical notation, times some variable x plus alpha, Greek letter alpha. Once again, this is the y-intercept, which when we looked at this in algebra was a b. So y equals beta x plus alpha, y is equal to some slope times x plus some y-intercept. Keep in mind that the slope, beta, is equal to rise over run. So beta refers to how much y should change for every 1 unit change in x. So if beta is positive, we would expect that for every 1 unit change in x, we have a positive unit change in y. And if beta is negative, we would expect that then we have a 1 unit positive change in x leads to a beta negative change in y. So basically what happens then is you feed in your data points into the regression model, and through a complex mathematical algorithm, which we're not really going to cover in this class, the computer is saying, well, based on the data you have, what is the line that best captures or runs through those data points? So you can see here in kind of the video that there are a series of different lines that you could possibly draw. There's really an infinite number of lines that can be drawn through any scatter plot. The computer or the algorithm is trying to figure out the best line that runs through these points. Now, most people that look at the scatter plot would say that that line should run somewhere from the bottom left to the top right to reflect a positive relationship. But even then, it's not entirely clear what the y-intercept and slope of that line should be. So you can see here I've drawn a couple different lines that may capture that data. So the computer is trying to figure out through the algorithm what is the best fit line. When we say the best fit line, which we'll explain a little bit more in one of the subsequent videos, versus the line that minimizes the variation of points around the line. That is to say, if we were to use the line to make predictions about the data that we've observed, which line produces the least amount of error in those predictions. So for the example here, I've run the regression analysis, and when you run the regression analysis, it returns to you the best fit line for the data that you have. And we call then the output our estimates of the slope and y-intercept. So you can note here that I have y hat, which is our prediction for y, is going to be equal to beta hat, which is our estimated slope, times x, plus alpha hat, which is our estimate of the y-intercept. So what we're really saying here is that when we model this, we're going to get a prediction for y hat equal to our slope estimate beta hat times x plus our estimate for the y-intercept alpha hat. I put the regression results on top of the line here. So if we were to write this out, we would say that your final exam score would be equal to 0.98 times your midterm score plus 1.05. So now that we have slope estimates and a y-intercept estimate, we have a estimate for the line. Final exam is equal to 0.98 times midterm plus 105. We can use that information to do a couple things. First thing we want to know is that line actually a good assessment or a good fit for these data? That is with statistical hypothesis testing. Now that we have these results, can we say that this line accurately characterizes a positive relationship between those two grades, or is that line statistically indistinguishable from a flat line where there is no relationship between midterm grades and final exam grades? The other thing that we'd want to know is how do we use this prediction line to actually make predictions about students' grades? So basically what we can do is we can plug in midterm grades and solve using our slope coefficient and our y-intercept to generate a prediction for each student's grade, or even for students that haven't taken the class. We'll cover those aspects of regression modeling in our next couple of videos.